Hello everyone, my name is Zhongcheng Zhang, a first-year PhD student in Institute of Computing Technology, Chinese Academy of Sciences. Today I'll introduce the OCCAMY, a sharing SIMD call process that can dynamically change SIMD length across multiple CPU cores. Over the past years, the length of SIMD instruction set has become longer and longer, while SIMD instructions have become more and more flexible, with the feature-left predicates, gather scatter, and Vig agnostic. The advancements give SIMD process more potential to accelerate program execution. However, the instruction sets are often implemented as private architectures, with each core having its own SIMD components, and this architecture usually has a low utilization. This is because there are a lot of scalar and memory-intensive programmers, which cause the idle length and idle cycles, respectively. To improve SIMD utilization, there are two sharing strategies. One is temporal sharing, which allows a core to use all the SIMD lengths, and the other is static spatial sharing, which can statically partition all the lengths and assign different partitions to the different cores. Obviously, they all improve the utilization, but they still have some limitations. The temporal sharing, since it does not partition any hardware resources, such as register field, leading to a reduced issue rates due to resource competition. And another one, although it statically partitions hardware resources, it still results in a low utilization because it does not consider a change in program behavior at runtime. In short, they all lack the ability to dynamically partition the hardware resources among the core running workloads. So, this is our question. To further improve the SIMD utilization, can we dynamically partition the hardware resources among the core running workloads? The answer is yes, but it used to be very difficult because the length of instruction set was fixed. But as we follow the development of instruction set, we found the least three all-over vector length agnostic features, which means that we can modify only the vector length without modifying the code. It makes the whole thing feasible. So, we have designed a new execution model based on SVE and static spatial sharing. It can trick the changes of program behavior, divide the program into different phases, and dynamically partition the hardware resources at runtime. As shown in the figure, it can take the utilization to the next level. But how do we achieve it? Firstly, we need an ISR as an interface to the hardware and software. We call it EM-SIMD ISR. Secondly, we need an elastic reconfiguration call. It has a result table to record phase behavior and SIMD length and some necessary information. And it consists of a few homogeneous function units that can be assembled into SIMD data paths of varying weights according to the result table. Thirdly, we need a line manager to generate a line partition length for each core based on the phase behaviors. Finally, we need a compiler to identify the workload phases, analyze the phase behavior, insert SIMD instructions in legal points to pass phase behaviors to the result table and request for the vector length reconfiguration. Okay, this is the design of the OCCAMY. Let's take a deep look at these components. According to our design, we designed 5 dedicated registers that can be read or written with MSR or MIS instructions to record the relevant information in result table. They can be divided into 3 categories according to their role. The first one is phase behavior. We use operational intensity to represent it and store it in the OI register. The second one is line partitioning length, which is stored in the decision register. And the last one is used to reconfigure vector length. It contains the VL register for the current length, the status register for the reconfigured success status, and the AL register for the available length. This is the microarchitecture of elastic reconfiguration core. In this picture, we have designed SIMD execution units as a set of homogeneous basic execution units, with each performing 128 bits SIMD operations, and the register file is partitioned into n blocks. Each execution basic unit is contained to a reg block. In addition, we introduce 3 tables. The first one is result table in the manager. It records the 5 dedicated registers for each core. The second one is the config table in the dispatcher. It records the ownership of an execution basic unit. Similarly, the config table in the register field records the ownership of a reg block. At runtime, OCCAMY can dynamically build assembly data paths for a call. Once an EM assembly instruction writing a length to a VL register has successfully executed. After that, both assembly compute instructions and load store instructions will be executed at this length. Next, I will show the execution of these instructions through 3 examples. Firstly, all EM assembly instructions are execution in order in the manager shared by all the calls. When the manager receives the write VL instruction MSR VL3, it will update the VL, AL, and status register in the result table, free all the execution basic units and reg blocks, and assign 3 execution basic units and their associated reg blocks to call 0. Secondly, when the dispatcher receives the FID instruction from call 0, it will dispatch 3 identical MILPs. Each MILP routes to an execution basic unit owned by call 0 according to the dispatch config table. Each execution basic unit fetches the operates from its reg block, computes on them, and produces a 128-bit result. The results from 3 execution basic units are written back synchronously into 3 physical vector registers. Thirdly, when a load instruction reaches dispatcher, it will append it with the width of its memory access according to the dispatcher config table, and the LSU will request 384 bits data from the vector cache and store the data synchronously into 3 physical vector registers according to the reg file config table. Similarly, SVE store instruction is handled. The next is line manager. It needs to handle 2 problems. One is how to predict the performance of the workload for a given number of execution basic units, and the other is how to partition all the execution basic units across all the co-running workloads. For the first problem, we can predict the performance using a roofline model. With it, we can know whether the operational intensity of the phase has a performance gain on the given number of execution basic units. After that, we can use the grid algorithm to partition all the execution basic units. Firstly, one execution basic unit is assigned to each workload currently executing a phase. Secondly, the algorithm iteratively assigns the remaining execution basic units to those workloads. In each situation, if a workload has a performance gain in the roofline model, it gets an execution basic unit. For example, in iteration 2, all the calls get an execution basic unit. But in iteration 3, only the last 3 calls can get an execution basic unit because the call 0 has no performance gain. We give 3 execution basic units. Finally, it terminates when all execution basic units have been allocated, or no workload can have further performance gain even when given more execution basic units. In addition, in order to improve the accuracy of the roofline model, we also modded multiple byteways. If you want to know more details, welcome to read section 5 in our paper. The last one is compiler. It also needs to do 2 things. Firstly, it needs to insert EM assembly instructions to communicate with hardware. In the control flow graph, we can see it inserts the blue instructions in the prologue and epilogue. They are used to pass operational intensity and trigger a line partition. But the former one passes the operational intensity of current phase, while the later one passes the OI of 0 and sets the assembly length to 0. And we can see it inserts the yellow instructions to monitor if the value of decision register is the same as the currently length. If it's different, it will span to configure a new assembly length and continue execute after successful configuration. Secondly, it needs to generate actual code to guarantee correctness. After it has received a new vector length for reinitializing the assembly register containing loop events for the new assembly length, and computing the partial result for the reduction variable obtained so far. We have implemented OCCAMY based on GEM5 and LVM13 and evaluated all 34 workloads from 28 hot loops in spec and 14 kernels in OpenCV. For statistical purpose, we put the memory-intensive applications in call 0 and computing-intensive applications in Core 1. After our evaluation, temporal, static, and OCCAMY outperformed private by 1.199 times, 1.109 times, and 1.391 times execute on Core 1 while faring similarly as private on Core 0, since they can assign more assembly lengths to computer-intensive workloads. And OCCAMY is the best performer by adopting a more flexible sharing policy that requires little hardware resources. Obviously, OCCAMY also have the highest assembly utilization as shown in the figure on the right. In the end, we mainly want to convey one point in this talk. We already know the SIMD instruction set have become more and more flexible over past years. However, much of previous research has mostly exploited these features from a hardware or software perspective alone, such as designing a new compiler algorithm to victorize more programmers. These are important, but as this talk demonstrates, hardware and software co-design is also a good perspective. That's all. Thank you.